Let's talk about isotopes. So we've already learned that a mass spectrometer will separate a chemically pure sample according to mass. And those different masses came from different number of neutrons. So those different streams in the mass spectrometer are different isotopes. In other words, if you have two atoms, for example, with the same atomic number, so it's the same number of protons, so it's the same element, but different masses, so it would have been in different streams because it has different numbers of neutrons. These are called isotopes. So let's look at this a little bit further. So here we have the periodic table, and you can see that we have beryllium highlighted here. Beryllium has a 4 above it, and that 4 is the atomic number. So to specify which isotope we're talking about for beryllium, we'd write it another way. We have the Be for beryllium, and the 4 is down here. And then this number up here, this 9, what is that? That's the mass number. So the mass number is the number of protons plus the number of neutrons. So that's going to tell you how heavy that particular beryllium isotope is. Because a proton and a neutron each weigh basically 1 atomic mass unit, so the total is 9. And then of course the atomic number down here, that is the number of protons. So this is redundant. When you have beryllium, it is always 4. If you have an atom with 4 protons, it is beryllium. If you have beryllium, it has 4 protons. But this 9 can change, okay, for a different isotope. But for this particular isotope, then we could figure out, well, if I have 4 protons, then how many neutrons must I have? If the total is 9, how many neutrons? Well, if the total is 9, 9 minus 4 leaves 5, so there must be 5 neutrons. All right, let's look at a few more examples. So here I have iron. Iron has 26 protons every time. Iron always has 26 protons. But the total mass of this particular isotope is 56. So 26 protons just because it's iron. But if my total is 56 with protons and neutrons, then my number of neutrons must be 56 total minus 26 protons leaves 30 neutrons. Okay, what if we had this same situation, iron 56, but we have a positive charge? So now we're getting information about the charge. Remember, the charge comes from protons, which are positive, and electrons, which are negative. So same as before, I still got the 26 protons. I've got neutrons. 56 minus 26 leaves 30. Now with the electrons, I must have more positive than I do negative. So I have one more proton than I do electrons. Well, I've already told you that we have 26 protons. So if I have one more positive proton than I do electrons, because I have this electric charge of +1, it must be my number of electrons is only 25. That would give me one more proton than electrons, so I'd end up with a net 1 positive charge. All right, we can have other charges. So here's 3 plus. We usually put the number first and then the sign. So 3 plus, which is looks a little strange, but that's how we do it in chemistry. So again, I've got 26 protons. I've got 56 minus 26 equals 30 neutrons. How many electrons? Well, 26 protons must be 3 more than the electrons, so the electrons must be 23, which gives us a net positive of 26. Because 26 is 3 greater than 23. All right, so you'll have some more practice with this in your homework. All right, one more thing about isotopes before we're done for today. Different isotopes are more abundant than others. And the atomic molar mass that's given on the periodic table is an average. So, for example, in a square on the periodic table, here we have chlorine. The 17 up above, that again is the atomic number of protons. But down here we have a number that's not as even necessarily. There might be some decimals depending on which periodic table you're looking at. You may have more or less decimals. But this is an average. It's an average mass. All right, where does this average come from? Well, we need to know what isotopes exist for the given atom. It's going to be different for every atom. Sometimes there'll be just one isotope, sometimes two, sometimes four, sometimes seven. For chlorine, there are two isotopes, um, chlorine 35 and chlorine 37. And those again are the total of the number of protons and the number of neutrons. So we could figure it out. You know, there must be 18 neutrons here because 35 minus 17 is 18. There must be 20 neutrons here because 37 minus 17 is 20. Anyway, but you can see there's more chlorine 35 than there is chlorine 37. Now this makes some sense because chlorine 35 is going to be lighter than chlorine 37, and the average ends up closer to the 35. Okay, so it makes sense, but how do we calculate it precisely? Well, for chlorine 35, if we know the percent abundance, so the length of this bar on the mass spectrum is just a little bit higher than 75. In fact, it's 75.77%. And the bar on this chlorine 37 is a little bit less than 25, so it's 24.23%. Those are the percent abundances. Then if we know the isotope mass for each one, so this is figured out in the mass spectrometer experiment, you can figure out the exact mass. Then how do we take an average? Well, we have to count this number more because there are more of these chlorine 35s and this number less. And you can do that just with the percentages. So you convert the percentages to a decimal. Your average mass is 0.7577 times the mass of that isotope plus the percent abundance of the 37, so 0.2423, times its isotope mass. Add those numbers together and you get 35.45, which is exactly what we had. All right, that's it for isotopes. And I hope that you enjoyed it and that you learned a little bit.